Hey, so yeah, welcome everybody. So we'll talk about performance of hybrid energy storage systems for underwater applications. So it's project number 9. So I'm Ariel, and this project is supervised by Karina, Yolan, and Ivan. So I'm based at KDH at the Department of Chemical Engineering. So a little bit of context, like the overall goal for this sub-project is actually to increase like the endurance and performance of AUVs. So in order to do that, we want to use like hybrid fuel cell and battery systems for power and energy systems. So one of the biggest challenges is actually to store hydrogen and oxygen in a clever way. So in my PhD, I'm working on like 2 different levels. One is like system design and modeling. So trying to answer some questions like, what is the best hybridization combination between the fuel cell and the battery, and which type of storage is better? And there is another level, which is like lab work. So I have like a small scale fuel cell setup in the fume hood at KDH, where I try to find the best operation conditions to run a fuel cell in a weird, like a closed environment, which is not that common for fuel cells. But maybe we should answer that question first, like why do we like fuel cells for AUVs? So this is the so-called Raguni plot, which is like the favorite plot of all electrochemists. So it shows you here the energy density, so the energy content of a fuel cell system and batteries and capacitors, and here the power density. So what we can see that the fuel cell scores very high in terms of energy density, so we can pack a lot of energy, so we can increase the length of the mission. But it scores quite badly in terms of power density, whereas battery do score quite well. So the idea of a hybrid system is to aggregate both high energy density of fuel cells and high power density of batteries. So that's like the general overview, and some milestone was like to optimize the design of hybrid systems. As I said, find the good operation conditions for a fuel cell in a closed environment, and also like try to find a strategy to share the power load between the fuel cell and the battery efficiently. And also thermal management of such a system kind of was a question that was raised, and we tried to answer those questions. So as I said, the first step was kind of to find the optimal combination of fuel cell power and battery energy content. So in order to do that, I kind of designed a sizing tool that find the optimum combinations of fuel cell and battery, and we can considers like the buoyancy compensation as well needed, because we are in underwater application, and it compares several types of hydrogen storage and oxygen storage. So for example, here we can see that those are results for like a 50-hour missions performed by Hugin, 50-hour-ish. So we can see that for the same energy content, the hybrid fuel cell / battery system with, for example, 700 bar compressed hydrogen storage or liquid hydrogen is way more compact than a full battery system, and can also compete with like a primary battery system. So primary batteries are batteries that cannot be recharged. So it's a one-shot, so to speak. And one of the major conclusions from that study is we can see that the hybrid systems, when they are optimized, they kind of reach an asymptote when the mission increases. So for example, here we can see the energy content of a secondary battery, so like the normal battery we have for like electric vehicles. So it's quite low. And when the mission increases, for example, up to 1,000 hours for a hybrid system with 700 bar compressed hydrogen, we can see that we score very high in terms of energy density and specific energy, which is energy per kilo. So it means that it proves that it is relevant to have such systems in order to increase emissions of AUVs. So I try to go a bit fast here. So the one takeaway from that study is like when the mission duration increases, it becomes way more relevant to have a hybrid fuel cell system than a full battery pack. Long story short. So now another like kind of milestones, like finding the best operation conditions for fuel cells in such an environment. So we're going to talk about purging. So here's like a scheme of what the fuel cell looks like. So you have hydrogen going in one direction, oxygen in another direction, and we produce water. And since hydrogen is kind of a fuel, this is what you pay at the end of the day, you want to save it as much as possible, right? So one way is to run the fuel cell in so-called dead-end mode. So all the hydrogen is trapped inside and has to react. So you have 100% of fuel utilization. However, you build up some water in the system and you accumulate some impurities as well. So you actually need to purge, so open the valve in order to remove the excess of water and recover the fuel cell performance. So I performed the design of experiments on a system I built myself. So it looks like that. So we have some fuel cell stacks from a Swedish company called MyFC and a bunch of sensors and valves. And the idea was to find a prediction model to extend as much as possible the time between two needed purges, and also to maintain the stack at a high level of performance. So that was kind of always trying to find a trade-off. And the major conclusions from that study is that, well, it was possible to find this prediction model and to predict the performance of a PEM fuel cell in a closed environment, working in dead-end mode. So the fuel cell should deliver like a relatively low current density. Forced convection should be limited, and the closed environment should be maintained at relatively high relative humidity. All right, and nowadays we're kind of continuing that project. We're trying a new purging strategy. So right now, like in the previous version, we were purging the fuel cell in only one direction. So the hydrogen was coming from the hydrogen tank to the cell 1, then 2, 3, 4, 5, 6, and then was leaving from cell number 6. Right now, we're trying a so-called symmetric purging strategy, where we reverse the hydrogen flow inside the cell after each purge. And nowadays, we're also like studying the behavior of each single cell within the stack. So the idea here is to compare the degradation between the two methods, so the single purging seen previously and the symmetric purging. So we have like some preliminary results here. So surprisingly, the cell in the middle of the stack kind of shows lower performance than the other ones. But something interesting is like the symmetric purging strategies seems to show like a more stable performance over time. So that might be a good way to operate the fuel cell for long range missions. All right, so that's kind of done for the experimental part. And now one very important question that was raised is like, oh, we have both a fuel cell and the battery system. So we have two energy and power sources. So how do we share the power load between those two power sources? So the answer is energy management strategies. Yeah, so the idea is kind of to design a system where we have like power profiles from real missions we've performed. And we have modeled the battery system and the fuel cell system. And here the idea is to kind of create like a brain, like an energy management strategy to say, oh, in that situation, we put more on the fuel cell or put more on the battery. So it's actually a collaboration with Clement and Chiche. So yeah, a couple of milestones here. We modeled the different components of a low-like energy system. We try different strategies using like real data, which is a great plus because such studies exist for like fuel cell cars or trucks because they have like standardized driving cycles, but you don't have that for underwater applications, unfortunately. So some goals is actually to decrease the total energy consumption, save some fuel, ensure that the AUV, like the AUV reliability. So if there is an upcoming obstacle or something that the AUV can go home. And I mean, the major requirement is actually to meet the power demand at all time. So I can maybe show you here better. So with Clement and Chiche, we actually built this big Simulink simulator with, so this part is actually simulating the hybrid system. So we have the fuel cell system, the battery pack, several like DC-DC converters. We even like consider the parasitic power losses due to because we don't have 100% efficiency in none of our systems. So this is what it looks like. And here we have like several energy management strategies that we try and compare to. And the idea is actually to find the best EMS for some types of missions. So I can show you like typical results we get. For example, for one EMS called fuzzy logic. For example, here we can see it was like a 7-hour mission performed by Hugin. And when we run the simulation, in blue, you can see the power demand. In orange-ish, you can see the fuel cell power, and yellow, the battery power. And here you follow like the battery state of charge, which is the energy content of your battery over time. So what your cell phone tells you, basically. So for example, we can see that here we have a very smooth like a variation of fuel cell power, which will lead to less degradation. But for example, we actually reach a very low state of charge. For example, it means that at that point, if we have an upcoming obstacle, we might not be able to overcome it. So the answer for those kind of studies is it is always a trade-off. And the idea is like, for example, missions with a very low level of uncertainties, like, oh, we go around an algae farm that we know exactly where it is. We will go toward management strategies that will save a lot of hydrogen, for example, because those missions will be run every day or every second day. So you want to save hydrogen and therefore money on those missions. But for missions with a high level of uncertainties, like going through under the ice or something, you want to save the battery state of charge and you want the AUV to survive. So it's kind of okay to consume a bit more hydrogen. And yeah, another question that was raised quite a lot when we had presentations, yeah, fuel cell system is, yeah, but what about the heat? Because the fuel cell does generate quite a lot of heat. And so it's kind of a general scheme of what we have. We have like a fuel cell system around 50, 70 degrees. We have several storage units like hydrogen and oxygen, and we have a battery pack that generates heat as well. And for a car or a fuel cell truck, it's actually very easy to add like heat pumps or heat exchangers to actually have dynamic thermal management. But in AUV applications, volume and weight is very limiting. So here the question, like the research question is like how to include like the heat balance of hybrid systems in the design process. So before we actually select a type of hydrogen and oxygen storage. So we actually did this big theoretical analysis. So for each type of storage, so liquid hydrogen, liquid oxygen, chemical storage of oxygen, compressed gas, or metal hydrate, we actually designed a fuel cell system for LOLO-like applications, so around 1.2 kilowatt fuel cell with 3 kilos of hydrogen. And on the graph, all the Q you can see is where heat happens. So Q tank H2, for example, that is the heat either needed or released when the hydrogen goes from the tank to the fuel cell. So depending on the type of storage we have, it can release heat or it can need heat. And so the idea was to do the heat balance for each combination of hydrogen and oxygen storage solutions. And so that gives us like heat balance, and it's a new criteria alongside energy content and buoyancy of the system to actually compare everything. So we decided to go for something called multi-criteria decision-making analysis with like objective ranking in order to rank and to compare all the different combinations. So those kind of studies are often used in like environmental sciences because as I said, we are comparing energy content, buoyancy, heat. So like watt-hour per kilo, buoyancy and watt-hour or heat. So the idea is to find an objective way to compare pears and apples, so to speak. So that was kind of the results we had. So we could rank each, we could get a weight for each criteria. So we have 5 criteria. So the 2 first ones are specific energy and energy densities. We have volumetric mass, and we have 2 criteria for heat. And we used 2 ranking methods. And we got quite similar results. And we could see that we like the three best ranked combination are either liquid hydrogen with liquid oxygen, or liquid hydrogen with compressed oxygen, or liquid oxygen with compressed oxygen. So there is like a high trend for liquid storage systems. And we kind of extended the analysis for what happened when the mission becomes longer, because we did this analysis for 50-hour missions, but we were like, oh, let's see what happens for missions from 1 hour to 1,000 hours. And we can see that the ranking kind of varies, but it kind of reach a plateau as well when the mission gets longer than 100 hours. And we can see that the ranking always remains the same. So even for long missions, there is a great interest for like liquid storage systems. So yeah, some major conclusions from that study that, well, the chemical storage solution, oxygen storage solution, which is called hydrogen peroxide, is not very suitable for such an application. And yeah, then we have like the major conclusion actually, which is that the fuel cell is anyway the major contributor to the heat balance. And then there is like little difference for all the combination of hydrogen and oxygen storage solutions. So it's actually mean that it is worth it to go for storage units with a high complexity, but high energy content, because anyway, we'll have to deal with the fuel cell heat. So yeah, going for more complex hydrogen and oxygen storage units is actually not a deal breaker, which was like the major conclusion from that study. Yeah, so now it's time to wrap up this presentation. So around this project, we got some publications, journal publications. The last one was 2 days ago, so I'm very happy about it. So yeah, we have like the sizing tool on the first part of the experimental work, and we could extend the sizing tool study to a fuel cell boat as well. And the plan is to submit a paper for the heat study quite soon. And we also contributed to a lot of conferences. And yeah, the energy management strategies were presented by Clemens in a conference a couple of months ago as well. But the work is not done yet for sure. So yeah, we will continue the experimental work on like symmetric purging strategies. And we will also work to improve the EMS and the Simulink model for hybrid systems. And yeah, we will also finish the heat study as soon as possible. Right. Thank you for your attention.